as to give the presenters their full amount of time that they're allowed. Let me introduce everybody to this session on carbon pricing. We have 4 papers that deal with aspects of carbon pricing. Our first presenter is Sahar Amidi. Her paper is entitled The Carbon Tax and Emissions Transfer, a Spatial Analysis. And so based on my reading of her abstract, my understanding is that she is going to be looking at the possibility that if firms are subject to a carbon tax, they may relocate their production in other places. I could be completely wrong, but I think that's what she's going to be looking at, and she'll be doing a spatial analysis of that issue. So Sahar, it is now 11:03, take to approximately 11:25, and then we'll go ahead and follow presentations immediately with Q&A then for about up to 5 minutes. So, if you are ready, you can go ahead.
Thank you so much. I want to talk about carbon taxation and emission transfer spatial analysis. I was working on this subject with my supervisors, Professor Nunez and Professor Isabelle Rabaud and other colleagues, Rezgar Feizi from University of Kurdistan. Let's begin with some essential facts. Actually, after the year of industrial revolution, extreme CO2 emission emitted by producing and consuming goods and services began to severe damage to the environment. So we have 3.9 billion ton increase in CO2 emission in the last decades. Some countries to tackle this problem contracted the Kyoto Protocol and Paris Agreement. So the special dependency between countries are important. Some countries, some governments implement carbon taxation, but some countries tend to import the goods intensive in carbon rather than producing them domestically with clean energy. Would normally tend to be imported from near country because in this situation they have to reduce fixed and variable cost of the production. In the last decade, we see increase of emission embodied in export and import around 5 and 10% respectively. Carbon emission affect the neighborhood through 2 ways. The first way is some countries try to produce their goods and services in their own region, so they pollute the environment in the national level and they transmit this pollution to the neighboring area through export. The second way is transferring the production of their output to tax-exempt or third countries. In this way, imported good from that country might be exempt from tax. There are 3 ways for using the input-output model is important. The first reason is exempt analysis can be carried out and serve as an effective tool in quantifying key coefficient change to CO2 emission. The second reason is dependency and proportionality relationship between different sectors can be captured in this model, and this model is very tractable. So we can see the interaction between intermediate inputs and final requirements in this sector, between the sectors. We have 2 questions in this research. The main question is, what is the carbon taxation effect in spatial account metrics approach, considering the direct and the indirect effect? And the secondary question is, which sector emitted more pollution through structural decomposition analysis? We try to use the structural decomposition analyze, multi-regional input-output table, and special account metrics model. Actually, we have 56 sectors, which we gather them in 5 categories. And we have 43 countries, which 31 of them are member of OECD countries, and 12 of them are other important countries over the period 2000 until 2014. Let's continue with some related literature. CO2 emission transfer is synthesized into 2 different streams. The first segment is CO2 emission embodied in trade that are gathered by goods and services produced in same country which are consumed in other country. And the next phase is carbon tax is physically in fossil fuel petroleum derived product, harvest wood product, curb and livestock. There are 3 ways for equalizing carbon tax across countries. The first way is all countries simply levy the same tax on the carbon content of fossil fuel product within their border. And the second way is the production tax base could be modified to include fuel imports tax to equalize them when production tax is lower in the producing country. And the final way is destination-based taxation. This way is very complicated. Let's continue with methodology. We have in the explained variable, we have 2 segments. Actually, we have emission embodied in import and emission embodied in export over the sectors I and J, and for the country R and S, I and J and R and S are not equal. For our explanatory variable, we have different categories. The first category is taxation variables. In this category, we divided our data based on 2 different segments. The first strand is before taxation, which is include total emission before tax, and after that we have after taxation, which contain the carbon tax, total emission after tax, and the tax impact on price. We have some control variables like GDP per unit of energy consumption and ratio of clean energy to total energy used and GDP per capita. Other category, we have some variables which they are captured from MRIO model, like intermediate in local and other region, final requirement in local and other region, consumer emission and producer emission. And we have the dummy variable for OECD countries. Based on some special test, we decided the fitted model in this research is special Durbin model. So this is our final equation, which y is explained variable and x is explanatory variable. Rho shows the special effects, and it is the special autoregressive coefficient. W here shows the white matrix, which in this study, we have 3 white matrices, but we decided to bring 2 of them. First of them is inverse of distance square, and the second one is the emission embodied in bilateral trade for the year T-1. And delta here is the special lag of our explanatory variable. This table shows the measurement and descriptive statistics of our variable. These 2 are our explained variable. Those are our variables which for the tax part, and these are for this category are for the control variable, and these are which we capture them from MRIO and dummy variable. Let's continue with the results. Our results divided by two different directions. In the first step, recall the secondary question, which it was which sector emitted more pollution in environment. And the second one, recall the main question. What is the effect of carbon emission through carbon embodied emission in trade? For answering the secondary question, we have 5 graphs. The first graph shows that during this period of data, we have increase in emission, but between the year 2004 and until 2009, we have considerable fluctuation. The right graph shows that emission increased during this period of time in the electricity category until the year 2012. But after that, we see a decline in this category. The first graph shows that the share of direct effect increased until the 2007, and it reached the peak. And after that, we see a slightly decline in our graph. The middle graph shows that we have the decline in residential building during the 2000 until 2014 for share of direct, indirect, and total emission. And for other sector, it doesn't change a lot, but share of indirect effect compared with other 4 category has the less pollutant sector in environment. This table shows the estimation of SDM model for emission embodied in import before and after taxation. Actually, the table was too long, so we decided to just bring some important variable. And because of the time consuming, we just bring the import table. We put the export table in appendix. If you are interested, we can discuss about it in Q&A part. The first and the third column are based on inverse destination square matrix. And the second and fourth column are based on emission embodied in bilateral trade. Row here shows the spillover effect. It means that the effects of emission embodied in import in neighboring country. As you can see, for all 4 categories, we have positive effects. So emission embodied in import will affect positively in neighboring area. But after the situation, in the situation after taxation, as we can see, we have less pollution. So tax has successful and it affects on environment. This table shows the direct indirect effect of SDM model for emission embodied in import. The direct effect shows the effects of independent variable under host country, but indirect effect shows the these effects on neighboring area, and total effect is the summation of direct and indirect effect. Final effect shows the difference between total effect of after taxation and total effect of before taxation. And as you can see, for GDP energy, clean energy, and GDP per capita, we have a negative effects, but for intermediate, local, these effects will be positive. And it's negative again for the final local and intermediate input in other region. And again, it's positive for final requirement in other regions, the consumer emission, but producer emission has a negative effect. Let's continue with conclusion. Our main results are the spatial spillover has a positive, significant, and acceptable sign, and tax increase in pollution emitted in trade. And our second results say that electricity and heat production is the most polluting sector, and residential building, commercial, and public service is a less polluting sector. Our conclusion: tax implements have been effective in emission embodied in import with considering trade metrics, but this effect is less tangible when considering the geographic distance metrics. The second conclusion is tax implement has been effective in emission embodied in export with the white matrix. When the white matrix is distance, but this effect is less tangible when we consider the trade as a white matrix. To sum up, the government can develop more rule when setting up the tax rate. And some policy recommendation. The first one is EU zone or other integrated zone should harmonize this kind of increase in emission. Secondary recommendation is there is a spillover effect before and after taxation, so the government should care about their decision on environmental taxation in their country and their neighbors. By and large, integrated regions are good to avoid the carbon taxation spillover effect. Thank you so much for your attention. I'm all ears for your questions.
Questions for Sahar? And feel free to turn your cameras on. I'm guessing we have enough bandwidth for that. It might make it a little more engaging for our speaker as well as for us getting to know each other. So feel free to turn your cameras on if you like. Okay, any questions for our presenter? If not, I'll ask a question or two. As I said at the beginning, we're going to allot at least till 11:25 for our first presenter. So we've still got a few minutes there. Maybe somebody will jump in with a question after I ask some of mine. So which countries were involved in your sample? Which countries were you examining?
31 OECD countries and 12 of other countries.
And all of these countries have a carbon tax?
Yes, actually based on the world input-output table, we chose the countries, and based on that, we categorize the sectors, and based on the sector, we created the carbon tax for different sector based on the implement factor of each carbon tax in different sector. So they has the carbon taxes.
Okay, just a thought here, and I don't know if this is a good thought or a bad thought. If you were to examine some of the countries that did not implement a carbon tax and look at how these variables changed, you know, there's always the chance that the trends that you observed took place independently of the imposition of the carbon tax. So that could be kind of a, you know, placebo test or something to see, you know, there should be no effect for the countries that did not implement the carbon tax. Is that anything that you think would be doable? Or
Actually, I'm afraid not, because our model is based on MRIO model. So in the input-output table, we have special 56 sector, and that sector for 43 countries. And based on that, we created our model. If not, we cannot use the 7 explanatory variables.
Okay, that makes sense. And my last question, then, again, I'll open it up if anybody else has any questions. Well, actually, I have two. One is, you had a variable reflecting the GDP per capita or something, reflecting the level of development of the countries in your model? In other words, countries that are more developed may show a different response than countries that have lower incomes. Did you look at that at all?
We bring the GDP per capita of the country as control variables, and we didn't look at the income of that countries.
Okay.
But it will be a good idea. Thank you so much.
Okay, sure. And finally, I haven't heard about input-output models in a while, but they usually assume a linear relationship between input and output. And we don't know if that relationship is linear or not, that underlies the relationship. So in the model that you used, are you assuming a linear relationship? And is there any concern that the relation may be non-linear?
Actually, here our model is linear, so our estimation and other things are based on linear model. But for the other input-output table, because it is good model for using the environment, if we use it for example, for the Kuznets curve, it is normal, which is not linear.
Okay, all right, thank you. Any other questions for Sahar? All right, well, I can see Marc Vatter is ready to go with our second paper. And so he's going to be talking to us about pricing climate change as a mortal threat. And so it's a pretty dramatic title, but Marc is going to be taking into account the fact that as with many other environmental threats, there's the possibility from a value of a statistical life perspective that we need to take that into account. And I think that's the vantage point that he's going to be taking as he looks at climate change and pricing of climate change. So Marc, we're right at 11:25. And so you've got at least 20 minutes till a quarter to, well, you're in a different time zone, so a quarter to the hour is what's available to you. Okay. That'll leave 5 minutes for Q&A. And again, if you run over by up to 5 minutes, that's not a problem.
Okay. Is the right-hand side of my screen blocked? Or can you see that?
I can see your screen. I believe we're going to see the entire screen.
Okay, great.
If I can't, I'll let you know, but I think we'll see your entire screen.
Okay, I'm Marc Vatter. I've got a trade name, the Economic Utility Group, and I'm an adjunct at Riviera University. I'm actually going to be starting a new job soon, but it's still a secret. So I'll let you know in a couple weeks where I work. So
Marc, we are getting on my screen.
Yes.
It's the left-hand side that's getting cut off a bit.
Okay. Okay.
And but I'm going to look at I'm going to look at my other view options. Okay, now I can see the left-hand side, and now I can see it all. Well, I could see it all a moment ago.
There we go.
Now, well, the right-hand side, I'm losing a little bit.
Oh dear. Okay. How's that?
Now it's the left-hand side.
Oh dear.
Actually, it depends on the user. Me, I see everything okay.
Okay.
It's not up to Marc for that setting.
Okay, I've just reduced my view to 50%. Now I can see it all.
Okay. So just to summarize what I'm doing, and I know it's kind of a verboten to read verbatim. Verbatim is verboten, but I have trouble getting away from it sometimes. So forgive me if I do a little bit of that. Mitigation of global warming and aggregate consumption here are chosen to maximize the product of expected lifetime and population. So that's my objective function. It's the product of expected lifetime and population. And I use a functional form that is constant relative risk aversion utility. And I estimate the parameters of that functional form using a panel from 220 countries over 29 years. And the conclusion is that optimal CO2 taxes are proportional to consumption per capita and therefore vary substantially from poor to rich countries. And it's not, so picking up on the last paper, it's not that, that you don't want to necessarily tax, impose tariffs to tax emissions content of the imports, but you have to go easier on poor countries and quantitatively much easier. And so I'll explore, and if you don't do that, you will likely do more harm than good. So starting with my objective function. So a lot of extant research uses a value of statistical life approach to value the mortality risks associated with climate change. And that approach should be used when risks are similar and small among the affected population. But Richard Toll wrote in 2005 in a survey article, I'll read this verbatim: differences in vulnerability will not only be observed between regions, but also within them. Some individual sectors and systems will be less affected or may even benefit, while other individual sectors and systems may suffer significant losses. So neither of the crucial conditions for application of the standard value of statistical life approach are met in the case of climate change. So I'm trying something else. And there are some precedents in the literature, but just fundamentally, John Broome writes about difficulty monetizing death when it is known with certainty that someone will die, rather than when there is a small probability that someone will die, as in the VSL approach. So in my analysis, I have two explanatory variables: consumption and temperature anomaly. And the optimum occurs where the effect on human lifetimes, that is life expectancy times population, of an incremental increase in aggregate consumption equals that of an incremental decrease in the temperature anomaly in global mean surface temperature, GMST. So I'm not claiming that the value of human life is infinite, only that it is the same whether life is attenuated by poverty or natural disaster. Here's my utility function. It is interpersonally comparable. If one person lives a year longer and another dies a year sooner, social utility is unchanged. I assume that utility is monotonically related to, as I said, the product of population and expected lifetime. And it's a function of aggregate consumption, C, and the temperature anomaly, T, which is global. Okay, so C is a national variable and T is a global variable. I estimate beta 0 and beta. Beta 0 is an intercept term. I use a fixed effects model with national effects. Random effects don't work, so I use fixed effects. And beta is greater than 0 with high statistical significance under a variety of assumptions about risk aversion. Sigma is the coefficient of relative risk aversion over consumption. Gamma is the coefficient of relative risk aversion over temperature. I started with a functional form from Weitzman, but but part of that, non-interacted terms are not statistically significant here. So you only see, I mean, you have consumption on the left-hand side, but it doesn't have a coefficient. So that gets moved over to the to the left-hand side in the estimation. And so on the right-hand side, you only have an interaction term. And when I added non-interacted terms, they weren't significant, so they're not here. Some of the properties of this utility function. One is that the marginal benefit of mitigation is decreasing in consumption. So this is climate justice. Poor countries have a harder time adapting to climate change than rich countries do. The marginal benefit consumption is also decreasing in consumption, which is very common for a utility function. But what's important to note is that this may offset, and I put that in quotes because I want to treat my interpersonally comparable utility function as with some humility. But this is important. This is the trade-off that we're examining. A poor country may want to mitigate climate change because of the climate justice property, but it also doesn't want to reduce its pay a high cost to mitigate because consumption, because of the diminishing marginal utility of consumption, which has to be sacrificed in order to do the mitigation. So the climate justice property will raise the average damage cost of emissions, but over globally, but you still may get a lower damage cost, monetarily speaking, in a poor country because of the diminishing marginal utility of consumption, which is very familiar property. Also, if consumption and temperature grow over time, then you get this annual discount rate, which equalize. It's implicit. The discount rate is a result rather than an assumption of the analysis, but this is the discount rate that would equalize utility over time, and it is increasing in growth in consumption and decreasing in the temperature anomaly. So this is a symbolic expression of the damage function. So the first equation shows the absolute damage function, and then the second equation shows damages as a fraction of consumption. And what's interesting here is that especially interesting, I guess I should say, is that the proportional damage function is independent of consumption. So, the damage function is linear in consumption, the absolute damage function is linear in consumption, and this implies stricter optimal climate policies in richer countries. So here's a numeric damage function to go with the symbolic one from the previous slide. And this is based on the panel estimation. So assuming normal errors, the 99% confidence intervals are narrow. I think I just did a little last minute testing, and the errors in the base case, the errors from all of these countries essentially tested as normal. I couldn't reject a null of normality. So there are 88 countries in this category, and there's quite a variety of them. And so, I mean, there's a concern that because climate and weather are chaotic, the assumption of normal errors might not hold. And there are countries where the null of normality was rejected, but you know, the chaos in these vital statistics, population times expected lifetime, could of course result from something like war. You know, it could result from something other than climate. So what's noteworthy here is that for the climate, for the countries where the errors tested normal, you have a variety of levels of consumption and a variety of population and a variety of latitudes. So it doesn't appear that the chaos of climate and weather in this, at least in this data set, is obviating the normal statistical assumption of normally distributed errors. The other thing to note here is that I tried this measuring consumption using purchasing power parity. That's the base case. That's the normal assumption. I use purchasing power parity, but I tried a case with market exchange rates, and the results were very similar. The results are robust to that assumption of purchasing power parity to value aggregate consumption. Another thing to note here is that the lowest discount rates accompany the highest damages, and this harkens back to the Stern-Nordhaus discussion. So we normally see that, but what's different here is that high risk aversion accompanies low discount rates because of its effect through the empirical estimation relative to what happens in the theoretical model. So sometimes a sort of a philanthropic person might be conflicted in choosing an assumption about risk aversion, because an assumption of high risk aversion is also a high aversion to current inequality, but in growth models like the Ramsey model, it gives you a high discount rate. So if you want to be compassionate toward poor people today, then you're sort of discounting future generations more, and vice versa. But because of this two-stage, this combination of empirical and theoretical models, when you change the theoretical assumption in the estimation, you end up sort of obviating that trade-off. So the philanthropist doesn't have to feel conflicted in this analysis. So here are some example CO2 taxes. Again, this is an economics paper, and you can't get to a CO2 tax without saying something about climate science. And so I'm making this assumption that equilibrium climate sensitivity is 2.5 degrees centigrade. You see the example CO2 taxes for the different quintiles of income globally here. You can see that because the distribution of consumption is very unequal, the optimal tax rates also vary a great deal from poor to rich countries. You might want to note here that this line showing emissions in 2016 indicates that the poor countries hardly emit anything, but emissions are a normal good, but not a superior good. So as you move from the low income or low consumption quintile to the middle income quintile, emissions go up. But then as you go from the middle income quintile to the high income quintile, emissions go down. So emissions are a normal good, but energy is a necessity, and economies at some point in their development start becoming less energy intensive and therefore less emissions intensive. But at the bottom of the distribution, there's hardly any emissions at all, and the optimal tax rate on emissions is very low. So practically speaking, you might not want to impose any kind of tax on emissions in poor countries, depending on how difficult it would be to do that administratively. So here are some example countries, and you'll note that per capita consumption in the United States is actually higher than in the upper quintile as a whole. And so you see that the optimal taxes in the US are higher than in Mexico considerably, and they're somewhat higher in Mexico than the world average, although I want to emphasize that in this model, the world average doesn't actually have a direct policy application. The main result here is that you need to differentiate, you need to tax discriminate or price discriminate across countries in order to maximize this objective function of population times life expectancy. And so you would see here leakage of emissions from the United States to Mexico would surely occur, but as part of a process that maximized the extent of human life. So that would be okay. You might not want to ignore the emissions content of goods coming from Mexico to the United States, but you wouldn't want to tax them at the same rate as emissions in the United States. And because of the proportionality of the damage function, by the way, it's also very convenient for you can assume something else about the response of temperature to emissions, and this is essentially the anthropogenic component of climate change. So I've got 2.5 degrees centigrade, but you could assume 5 degrees, and that would essentially double these numbers. I saved this for last because I wanted to make sure I had time to do something like this. How much time do I have, Peter?
You're in good shape. You have till 11:48, so you've got a good 3 minutes, and we'll give you a few minutes more if you need it. Okay, I'm going to run through a derivation here because I think this is such an interesting result. Suppose you have two countries. You have equation 3 here is the marginal utility of consumption in each country. Equation 4 is what would be a uniform tax. So if you optimize this utility function globally and derived a uniform carbon tax, you would essentially plug in C bar, which is in this model, average income or average consumption across the two countries. I normalize that to 1, makes this derivation easier. But without loss of generality, country 2 is richer than country 1. So consumption in country 2 per capita is higher than 1. Consumption in country 1, assume they have the same population. Consumption in country 1 is lower than 1. So if you combine these two, the change in utility in each country from paying this uniform tax is here, given by equation 5. And under the objective function, the change in social welfare globally by payment of the uniform tax is shown here in 6, which of course is negative because we don't have the benefits of mitigation yet. It's just payment of the tax. And then here in 7, you have the marginal utility or unit of warming, which is negative mitigation. So this is negative. In equation 8, you get the change in social welfare from mitigation, which is positive. And then you can combine the two, the change
in social welfare from payment of the tax with the change in social welfare from the mitigation. And so this is kind of interesting. If you impose a uniform tax, in this theoretical model with the empirical results that I have, which are quite strong, the uniform tax actually lowers social utility. And again, this is not the normal objective function. It's not a Calder-Hicks total surplus value of statistical life objective function. It's a Bentham and Mill utilitarian function estimated using these vital statistics, population and life expectancy. But what it says is, so long as people are risk and inequality averse, so that's a pretty minimal assumption. And given the econometric results, which are quite strong, beta hat greater than 0, equally weighted utilitarian social welfare, that is total human life years, decline, as I have measured it empirically, declines with imposition of the uniform carbon tax, despite property 1 of the utility function, despite climate justice. That is to say, denial of anthropogenic climate change would be better than imposing this uniform tax. Climate change is deadly, but climate policy must be sufficiently progressive or it will be more deadly. And that is my main result from the model. But in terms of specific policy implications, emitting fuels should be taxed or regulated at or near the point of consumption rather than at the source. Rich producing countries should continue to produce where crude oil and refined products and liquefied natural gas, which are all traded globally, and therefore their prices are tantamount to a global tax. And as long as the marginal costs come in below their globally determined supply prices, which are reduced by whatever the appropriate carbon tax is in each country, even as emissions in those countries are reduced considerably because those countries are wealthy. So the point here being that, as I've written here, when CO2 emitting fossil fuels and other goods are used in poor countries, they may extend human lifetimes in ways that marginal uses in rich countries do not. And the estimates in this table would incent relative increases in consumption of all goods, including fossil fuels, in poor countries, with relative decreases in rich countries. And I'll stop there and take questions.
Thank you, Mark. Does our audience have some questions for Mark?
Yep. Can I ask a question?
Sure.
Hi, I'm Yefan. I'm from Tsinghua University, and recently I'm doing some research of the club, using the club series to dealing with the climate change problem. And I like your one sentence from your presentation, like both consumption and climate affect mortalities, because for a long time I when doing my research I use yes, that's where they're from, and I think the consumption, the climate is a function of consumption, and which is the same in the not horse in the death model, and but your word opened my mind. And I have like 3 questions. First I will start with the small one. It's like, what's the discount rate you're using in your model? This is the first one. And the second one is like the free riding. It's always happens in the world. And how do you think of the free riding in your model? And the last one is like, I think you're talking about the mortalities. Mortalities is the function like is the health conditions. And what I learned from my study is like what I'm thinking. Maybe I didn't grab that point in the not horse like the climate club the paper, he didn't talk about the vulnerabilities in that model, like the club model. So that will cause, like, even we use the same tags for the different region, that's because of they have the fundament, they have the different base of the vulnerability, then that will in fact for the different people. And so maybe is that a good step to using vulnerabilities to the health vulnerabilities to do the further study in the climate change studies? Thank you.
Yeah, thank you. Let me start with your first question. So the discount rate here falls out of the model. It's not an assumption, but it's implicit. So in the right-hand column you see implicit real discount rate, and so this is the rate that would equalize the present value of utility over time. And again, it tends to be higher when you have lower values of the damage function. Again, hearkening back to Stern and Nordhaus, but but risk aversion really plays a very strong role independent of that. So, but again, you in this model with the combined theoretical and empirical models, you don't have that sort of vexing trade-off between your altruism toward poor people today and future generations.
Yep.
Okay, and so your second question was about free riding. Of course, free riding is always possible, even here. There is, I mean, the optimal tax in each country is generally non-zero, although I would say, practically speaking, you know, given any administrative or transactions costs that I am neglecting in the near term, it might not be worth it to try to impose any kind of policy in poor countries. They hardly emit anything, and the policy would be pretty gentle. So, but as you can see, I mean, the optimal taxes are perhaps lower than what you're used to seeing. And again, they depend on your assumption about the anthropogenic component of climate change, but they're non-zero. So you could always, as a country, you could always free ride, right? You could just not have a climate policy, and you wouldn't be doing your share. But the point here is that you can perhaps, if we define free riding as having a policy that imposes an implicit a shadow price on restrictions or a tax that's below the world average in your country. I mean, if you're already poor, I mean, that's too harsh a definition of free riding. You really need to go easier on poor countries and be stricter in rich countries. I mean, it's the difference between sort of these guys who are using propane to do their cooking or whatever, and somebody who's choosing whether to drive a Suburban or a Corolla in a rich country, right? I mean, this use may actually affect the health and well-being of the people in the household, but driving a Corolla instead of a Suburban probably won't shorten your lifetime. And that's the contribution of this analysis. And now your third question had to do with, I'm not sure I quite understood what you were asking, but you were talking about mortality and health measures and this sort of thing as a measure of human welfare.
It's like the health vulnerabilities. It's like it's different in American or in Indian. They're different.
Exactly, right.
Yes.
That's the point. And so, but I'm just measuring it as, simply, that you could improve on this, right? but I feel like what I've done here is an improvement on extant research, which uses this Calder-Hicks criterion based on the value of a statistical life. So maybe this is progress. You might refine it using other measures of well-being, but I've just got longevity. You could take life expectancy alone without population, but of course then, Liechtenstein would count the same as China, which is ridiculous. So I multiply life expectancy times population, which that may not be perfect either. You might want some kind of interior combination to sort of indicate quality of life as opposed to sort of the length of it. But I don't know how you would do that. And because life expectancy is in the objective function, you're not going to get into a Malthusian nightmare, right? I mean, if you're in a Malthusian state, then probably your life expectancy isn't very long. So if you get out of the Malthusian steady state, you probably will increase the objective function that I've defined.
All right, thanks very much to Ye for his questions and Marc for his answers. We're going to move on to our third paper by Petr Spodniak, and the title is Analysis of the Historical Pass-Through of Carbon Costs to Electricity Prices in European Power Markets. So the title seems pretty self-explanatory, and so we'll see what it has to say about how pricing carbon affects electricity prices in European power markets. So Petr, it's all yours. We're coming up a minute or two before the hour, so you have till about 20 minutes after the hour. That'll leave 5 minutes for Q&A. Again, if you run a few minutes long, we should be fine.
Thank you very much. I'm trying to share the screen now, and let me please know if you can see my screen.
Yes, I can.
So the presentation is on. Okay,
Yeah.
thank you very much. Yeah, excuse me.
Can you put, okay, it's on presentation mode, but we see not the full screen, but the other one, but the other screen, with the mixed slides.
Okay. Oh, sorry about that. Let me try again. Controls. Somehow lost the option to. Can you still? Okay, new share screen one. Maybe if I just share the whole screen. Is it the same?
Yeah, we're back to where
we were. Okay.
we were.
So one last chance. Sorry for the delay. So and the slides on. And
That's good. At least it's good for me.
right?
Yeah, that's good. Thanks.
Okay, thank you. So hello everyone, my name is Petr Spodniak. This is a joint work with Fabien and Roques, and the title is, or the paper is focusing on the historical pass-through of carbon costs in European electricity markets, but we specifically focus on France in this presentation. Here you see the structure of the presentation. I will first briefly show you the key findings for the spot and forward markets, but then I will go back and motivate the study, provide you some context, then describe our methodology and show the results and final conclusions. So the key findings of the study, as I said, we focus on France and the carbon pass-through rates in electricity prices in two different markets. So we look at the spot market and the forward market. And when we look at the comparison between the two, we find in using our simple econometric approach that in the spot market, using the simple econometric approach, the results are not that robust, and we find a pass-through rate of about 0.5 to 0.8 value. But then we do a more robust analysis for the forward markets, and we find the pass-through rates of approximately below 1, looking at a time period of 2011 up to 2020. So a long time period for, given the EU's history of the EU ETS system and its price path. But this is just to give you a first bite into what's coming, but I go back and start motivating this research. So why we talk about carbon pass-through rates, it is about pricing externality, which has been done in various forms, in varying scope. For instance, we can price upstream, we can price downstream, consumption, production. We can price different sectors. So the coverage of carbon emission pricing can include ETS sectors or non-ETS sectors in Europe. And also it is done regionally, nationally, continentally, like the ETS system in Europe. So there's a varying form of pricing carbon emissions. Why this topic is important? Because it has a relevance for competition policy as well. As we said, if carbon pricing is quite different in one region than in the other, this may lead to carbon leakage, which would mean that the economic activity would shift from one region or area, or economic activity into other jurisdictions with different carbon burden or carbon cost burden. This is being trying to be avoided in the EU. For instance, recent mechanisms or schemes were adopted, such as the compensation. Well, one is the compensation schemes. So member states in the EU can compensate some electro-intensive industries for part of the higher electricity cost induced by the carbon price. And this is the motivation of this paper as well, to quantify what this compensation would be for such industries. Another mechanism that has been recently developed or adopted is the Carbon Border Adjustment Mechanism, the CBAM, which is a levy. It's a planned levy in the Europe to apply a levy on imported goods into the EU. So this is still work, not a legal obligation yet, but this is a mechanism that is being currently developed and will be probably applied in specific form in very near future. On the right hand side in the bottom, you see why the carbon leakage can be meaningful, because you see a carbon in trade. So how much carbon emissions are embodied in exports in different regions of the world in the years 2005 and 2015. So we see that different goods exported carry quite different carbon contents, and this is different mechanisms such as those I mentioned try to address these differences and to establish a level playing field. This study looks at France as one of the EU's countries, and we look at the pass-through rates in electricity prices over different periods. So when we look at the forward market, we look at a time period of 2011 to 2020, but we also look at the spot market results for a little bit shorter period, 2015 to 2020. So just to make the definition of carbon pass-through more specific, it is a proportion of carbon prices, so euro per ton of CO2 passed through into electricity prices. It can be interpreted as a proportion of higher costs incurred by end users of higher electricity prices attributable to a carbon price. So it is and this is why only it is kind of an indirect cost that the electro-intensive industries can then claim back in a sense, and member states can compensate those electro-intensive industries for this indirect cost caused by this carbon emission prices. So we asked 2 questions: have these carbon costs have then been passed into electricity prices in France? And another one is to what extent? So quantify what are the values of these pass-through rates in France. The contributions of the study are that we want to shed light on a French specific carbon price pass-throughs, but which is part of this Central Western European region. We want to look at the drivers of those. There are many fundamental changes happening during the studied period, so we want to understand the fundamentals, the market changes, and provide some quantitative evidence, put some values into this. So the context, I won't go into details. I think many of you are familiar with the European Union's emission trading scheme or trading system. It's the world's first biggest major carbon market. It is a cap and trade system established in 2005. And what its purpose is to in the short term facilitate cleaner fuel sources, fuel switching from dirtier to cleaner fuels, but in the long run, it tries to incentivize investments, promote low carbon investments. There have been different phases of this system, and different phases were defined by different fundamental market regimes, you would say. Let's say in phase 1, in the introductory phase in 25 to 27, there have been over allocation of free allowances, which led to the price crash. Then in 28, we had a financial crisis, but from 2013, we have started to introduce some mechanisms to avoid those problems, like backloading of auctions and market stability reserve mechanisms. So you have seen a large price evolution of this market, being €5 per ton of CO2 in 2016-17, and currently being over 50 euros. So it has been it has grown tenfold during this 4 years time. Here, I just wanted to quickly motivate why this is relevant. I said that this is member states in the EU can actually compensate for this carbon burden for electro-intensive industries, and this is defined in the Commission's journal. There's why this is defined, what is it trying to do, why we want to compensate some of these industries, is that we want to minimize the carbon leakage, as was discussed, cost-efficient decarbonization, and minimizing the distortions of the market. So these are the reasons why the EU or the Commission is willing to compensate some industries for this. Obviously, this has to be in line with the state aid rules, not disturbing the competition. And here you see a formula how, or from the original communications of the European Commission, that the aid intensity is actually based on the emission factor, the C component there, that is represents the share of an increase in carbon prices that is passed through to power prices. So, and this is the C is the key factor that we want to know, so we can quantify and understand, for instance, the compensation mechanisms. From literature, we could maybe structure this into 3 different strands. Theoretical models, they try to focus on the carbon pass-through into electricity prices through different dynamics, or studying, for instance, competition, demand elasticities, the merit order or supply functions, and there are several studies on the top of the table that you see in front of you. Then other types of studies, model the market or simulate model the market fundamentals. So they leverage on the market fundamentals, but modeling the system from bottom up and simulating the impacts of carbon prices. There are somewhere in the middle of the table, you see some studies doing simulations with Times model, or there's other studies using Primes model, and so on. And the final strand is our econometric literature that model typically, well, there's some OLS regressions and often as time series models using daily or hourly spot or forward prices, finding different carbon pass-through rates in different market areas. So this is just to give you a quick overview, and I won't go into details of those. I mentioned this study is following a very simple methodology, but one thing, so we want to control for structural breaks. As you will see in a moment on a figure, the prices have been developing quite rapidly, and they are underlined by very fundamental changes in the market. So to control for those structural breaks, we follow a methodology to identify those breaks in the time series. So our approach is just falls into the econometric type of literature. The first point on the structural break, we use this Andrews methodology when we split the samples into two subperiods, before the time t and after, and we just test a hypothesis whether the coefficients b1 and b2 are equal, and then we use the Chow test in the quant likelihood ratio statistics, which would give us a significance of whether the structural break is present or not. So that's kind of a first approach of our method, that we specifically control for those breaks. And second is a simple linear regression type of models for spot and forward. They are very similar, and we control for the key fundamental variables like fuel prices, so gas and coal. In the spot model, we control for the residual demand or residual load, and in the forward model, we have some dummies for years. So without further delay, we would first have a look at the spot price model results, and I wouldn't interpret too much this figure, but this is an hourly time series from 2015 to 2020. The red line shows the power prices in France, and it's marked into on the left-hand side y-axis. Then what is important here to show are also the shorter marginal costs of the fossil fuel type of generation. So these are the coal and gas power plants. And this figure is not too readable because it's quite high frequency and too long time series, time span to show. But the point here to make is that there's a changing dynamics between which type of fossil fuel generation are, let's say, profitable or yes, profitable, which is driven by the carbon price. I don't know if there's a big noise. Let me know if this is disturbing in the background. And the yellow line is showing the residual demand, which is the demand in France minus the generation of wind, solar, and the nuclear, and that demand is actually quite small because of the large nuclear generation in France. So just going into the simpler results of spot market model. We split the 6-year time period into 4-year periods. So you see that some of the fundamentals having their positive coefficients significant. But the most important variable of interest is the price of CO2, which would give us the carbon pass-through into the wholesale electricity prices in France. And you see the variation is between approximately 0.5 to 0.8. So the interpretation of this is that when we increase the CO2 price by €1 per ton of CO2, we would expect the electricity prices to rise by 0.5 or 0.8 euros per megawatt hour. The issue with the spot price model using this simple linear model is that the coefficients and the models are not robust, not stable, sometimes providing counterintuitive results. And so why we went for the forward model, which you see here. What you see in front of you are the evolution of forward power prices and the shorter marginal costs. So again, showing the shorter marginal cost of the gas and coal power plants. And here you see, so this figure is a little bit more readable than the hourly figure. So this is in daily frequency. And the green line shows you the carbon price evolution as well over the last 10 years. What you see, what I would like to note first, that you see that the profitability of these fossil fuel plants has been changing during the time when we look at the shorter marginal costs, when gas power plants were much more expensive to run in the period of until 2016-17, but this dynamic has changed approximately in 2018, and again you see that the relationship to the increasing carbon price over there, when actually the coal's shorter marginal cost are way above the gases, and you see this fuel switching happening in the recent time. This figure also shows the estimated emission factors, so the carbon pass-through rates. Visually, you see the colors. The green one show the relatively low pass-through rates of around 0.6, sorry. The yellow or even lower, 0.5, and the red ones are the highest one. Why this time period is split into those 8 subsamples? These are the results of the structural break analysis, and there are many reasons, fundamental reasons why even the statistical test identify these structural breaks as breaks. There have been many things happening in France, such as a large nuclear, not shutdown, but because of some technical issues in the France nuclear fleet, there were very big regime shifts during this time period. But I won't go into detail about discussing all these detailed subsamples, but this is also important to understand those. Here you see the same result, but in the regression table. The key is there the pass-through rates of the CO2 prices by the sub-periods, and it varies from 0.5 to slightly over 1, and the interpretation being the same as I mentioned before. So increasing the carbon price by €1 per ton of CO2 would translate into let's say 0.5 in euro per megawatt hour of in electricity price increase. And this would be let's say the values, the carbon content, the pass-through that, for instance, would go into the reimbursement equation that we had a look at in the beginning. So just to conclude, what we did is we look at the pass-through rates in one single country, in France. But what is maybe the added value, without explaining you all the details of the fundamentals, the controlling for the structural breaks gives very valuable information, and also controls for better specification of the model. Using a 10-year time period is also a contribution, because this is very long sample. We quantified this pass-through rate, being in the forward market about 50 to a little bit over 1. You probably realize this is a simplistic linear econometric model, so its benefit is this has a direct interpretation, usability, applicability in member states. I mean, commissions, definitions, or let's say defending some support mechanism, support compensations for specific industries. So it is simple and usable. Obvious weaknesses are that it's a linear model, and it can be the model can be made more complex, definitely, and probably more precise then, but maybe the complexity would not necessarily overweight the benefits of this. But nevertheless, the next steps are look at more complex models for the forward market in daily frequency. Some lagged models like VAR could work well, but again, the interpretation of the results should be attempted to be kept. Maybe for the high frequency markets, hourly markets, some gauge volatility type of models could be interesting to explore. Maybe the structural break approach could be improved or use alternative. And as I mentioned, the interesting story behind this type of study is to understand better the market fundamentals, maybe the market design changes. I mentioned two of these, this carbon border adjustment mechanism, for instance, and its impacts, but also maybe other regions in understanding the pass-through rates in different market types or would be interesting. So I would probably stop here if I'm not over time, and welcome your questions, please.
Looks like Regina has a question, I believe.
Yeah, thank you. Thank you, Peter, for this interesting study. I've got two questions. My first question is, I mean, you take the period 2011 to 2020, and I'm wondering, I mean, there was this big change from free allocation to auctioning in 2012 to 2013. So I'm wondering, like, we were looking more at the micro data of transfers in these markets, and our findings are that small companies might not have been very sophisticated in trading, and they might not have been aware of these opportunity costs when they got the allowances for free. And I think for your pass-through, they would need to be aware of these opportunity costs. So I'm wondering if you could see a change where there is this change from free allocation to auctioning. And then the second question along those lines is, there were all these studies you mentioned before already doing empirical research. Have you compared your results with those, and can you explain differences or similarities?
Thank you very much, Regina. Very important questions you raise. Definitely the market fundamentals that we didn't have yet time to discuss here are very important, and this is interesting that you mentioned about the microdata and the differences in how small companies use that opportunity to get the free allocations or not. And we haven't specifically controlled for this, but the structural breaks, we have a structural break in that period, so that would kind of capture that regime shifts. But definitely further detail could be we could have a look into that more specifically. And how our study fits into the other ones, well, try to first quickly review that there are different types of studies. So we fit into the econometric world, and quantitatively, actually, even though we use the simple linear regression type of models, the estimated coefficient is not, they are not really out of let's say scale for the European market. So if we specifically look at the, let's say, the pass-through rates, but there are big differences in which markets are studied and which is it forward or spot, and differences in the model specification. So indeed, this is a missing link. We should prepare a table with the key differences and how our results compare. But thank you for the recommendation. We will do that as well.
It looks like Mark has a question, but Mark, if it's a short question, because we'll need to get to our final speaker. If it's going to be a longer question, we might need to save it to the end. What's your pleasure?
I'll ask the question and you can decide whether to answer it right off, now or later. Does a pass-through rate higher than 1 indicate that the wholesale market is not workably competitive, or is that just something that's being defined inframarginally, and so the inframarginal units tend to get higher prices or profits?
Maybe, if possible, I would maybe keep that answer up till the end, just to be on the safe side. But it is an interesting question. Is it okay, Peter?
Yes, I think that's a good idea. I'm sure there are people who might stay around if things run a little bit past 1, and there'll be time depending on how much time Regina needs, but I want to make sure she has the full amount of time that all the other presenters have had. So our final presenter is Regina Betz. Her topic is how do firms respond to a rising carbon tax? And this time we get to hear about Switzerland. So Regina, it's all yours. 20 minutes will take us till 10 minutes to the hour. That'll leave 5 minutes for Q&A, and then any closing questions that people have on any of the papers.
Okay, thanks for this. I think, Peter, you need to stop sharing your screen. Yeah.
Oh, yeah, excuse me. Yep.
No worries. It was just not possible for me to start sharing. So is it, can you see my screen now? Yeah, perfect. Okay. So, well,
I may have spoken too soon. Right now on mine, I'm seeing how do firms respond to a rising carbon. I know I can adjust my screen here. Okay, I'm fine.
Yeah,
fine? Others see it all? Okay.
Okay. So yeah, thanks so much for bearing with me in my presentation. I'm the last one today, and here it's already 6:30 in the evening, so I hope nobody will disturb me in my presentation. So what I would like to explain or to present to you today is a paper which is with some co-authors, Dario Fauceglia, Thomas Lloyd, Tobias Müller, and myself. And actually it was handed in already last year. So it's published as a working paper. If you are interested in getting more details, you can find it on this website. And so I'm starting to give you a bit of the background, because it's the Swiss climate policy is not so easy, and it's important that you understand very well how this tax is actually working, or this levy we call it. And then I will show you a bit of the literature which has been published in this area, give you an insight on the data, what are our methods we were using, what are the main results, and then conclude. So carbon pricing instruments are becoming very common. but there's still a very controversial debate about, should you use a quantity instrument like a carbon tax, or should you go with a price instrument, or with a quantity instrument like a carbon market. So they are really, especially in Germany lately, where they were thinking of having the heating and the transport sector included, really big debates what to do. And in Switzerland, it's interesting because Switzerland has implemented a kind of a hybrid instrument. And I think Germany has now also followed this road by combining the price and the quantity instruments together. And so I think Baumol and Oates in 1971 were the first ones talking about this standard price approach. And the idea was that when you are setting a price on a pollutant or an externality, you don't know exactly how the elasticities are and how high would you need to set the price in order to reach a specific quantity in reductions in the pollution you want to achieve. So there is this trial and error what you usually need. And so the idea here is to combine a quantity and a price instrument. And so this is the really special case in Switzerland. And empirical ex post evaluations on the effectiveness of carbon pricing are quite rare. And what they find are that tax rates are usually too low to really have an impact on people changing their consumption patterns, or they have not been adjusted over time, so they stay quite low, or the effects have been basically lost in the noise of fuel price changes. So in Switzerland, we really have now data for an ex post microeconometric evaluation of a really substantially increasing carbon tax. It's now one of the highest of the world. And and we have this special feature of a hybrid quantity price instrument. This gives you an overview on where we have price and quantity instruments. And as you can see, I mean, the big green bubble here is the European emissions trading scheme, which is a quantity instrument. And here in the top range, so this is the level of these taxes. You can see there is the Swedish carbon tax, which is the highest, which is only on the transport sector. And Switzerland is not including the transport sector, but it's the second highest. And I think Liechtenstein has the same instrument. It's so small that it adopts the Swiss policy. And so we have now a carbon tax, or we call it levy, of 96 Swiss francs, which is pretty similar to the US dollar. And it's on heating, oil, and gas, so in industry and household sector. So it covers around 35% or so of the emissions in Switzerland. We also have an emissions trading scheme in Switzerland for the bigger industry, and it's linked to the European scheme. And so there we have other carbon prices. Right now, it was just shown by Peter, it's more than 50 euros in the industry sector for the EU and the Swiss emissions trading. So when you look at those which have a higher coverage, so here, California and Quebec, you can see those schemes have usually lower prices. So if you have very high tax rates, it's usually just a partial coverage, and that's what we have in Switzerland. So this standard price approach I already mentioned. How it works in Switzerland, it's basically that the Swiss government sets a quantity target. So they want to achieve a specific amount of emissions, and that is less than is emitted already. So they want to achieve reductions. And when this level is not achieved, so when the emissions are above that target level, they will automatically increase the tax. So the tax is basically linked to the quantity, and there are usually even two different levels which trigger then two different increases. So if it's a lot above the quantity which wants it to be achieved, it goes up for a higher amount than if it's closer to. So it's basically helping this trial and error to achieve a quantity with a price instrument. So our main research question is, what is the impact of the Swiss carbon tax, which was introduced in 2008? And we are only looking at the industry and service sector. We're not looking at the household sector. We don't have that data. So we're looking at energy consumption and carbon emission. And we do an ex post analysis. And we have panel data for the years 2001 to 2015. So we cover already the period before the tax was introduced in 2008. So our substantive sub-questions are, how did firms reduce emissions if they did? So we are looking at the substitution patterns between different energy sources. I'm not covering the second question. We have looked at this as well, but I'm looking at the other red one. So did the firms react on the tax or on the fuel price changes? Because the oil price is also moving very volatile. It's very volatile. So this gives you an indication how this policy mix in Switzerland looks like. I already said we have emissions trading, and we have this, we call it CO2 levy, because the money which is raised is basically given back. So it's not really a tax, it doesn't go in general budget. And some companies can also be exempted of paying this CO2 levy, or let's put it that way, they can claim it back when they show that they have reached a certain reduction target. This is called target agreement. And as you can see, some sectors like the cement sector, the pharmaceutical sector are covered, like a lot of emissions are covered. And also here you can see in the cement sector, it's also a lot of the company. So this, on this side, you have the percentage of firms covered, and here it's the amount of CO2 covered by each of these policy instruments. So as I mentioned, the Swiss tax has been increasing over time. It started very low with 12 francs in 2008, 2009. And so that means 885 francs for a terajoule in light oil and 673 Swiss francs per terajoule on natural gas. And then, as I said, there was these trigger points. So they were assessing if they achieved a certain reduction in emissions, and they didn't. So far, every time they checked, they saw that the tax level wasn't high enough, and so it triggered that it was increased. So it was increased the first time to 36, then to 60, and right now we have 96 since 2018. This is what you saw on the graph before. So looking at that, this is really a substantial increase of around 400% over that period of 8 years. So what does the literature tell us? So there is empirical literature, and so there have been estimates on what are the effects of taxes which have been levied in industry and so on. And they found reductions of 8.4 or 22.6% compared to others which were not under the tax. There have been studies on gasoline taxes. There have been actually more studies. And there has been also some analysis on the Swiss carbon levy. However, most of those were either based on models, so they were not empirically on macroeconomic data. They were rather with CGE models, and others were by questionnaires and surveys asking if they have been implementing mitigation options and so on. So our data is provided by the Swiss Federal Office of Energy, and it includes 1999 to 2015. We have more than 45,000 observations almost from more than 10,000 firms in the service and industry sector. We can derive the CO2 emissions, we have the energy consumption, we know if they were consuming light oil, natural gas, or even other types of fuels. We have the fossil fuel shares and also the net electricity consumption. And we added to this data firm characteristics, so number of full and part-time employees, firm size, these are all proxies to understand the size of the company, and also subsector affiliation. And then we also used some control variables like heating degree days, indicators for economic activity, and real oil price index. So when we look at the descriptives, you can see we have here the number of observations, we have energy consumption, CO2 emissions. So the mean is like 325 tons per CO2 emissions. Yeah, you have to bear in mind that there is also the service sector included. So the large ones, the upper parts are much higher if you go for cement industry, for example, or so. Carbon intensity, light oil consumption, share of light oil in percentage of the energy consumption, natural gas consumption, share of natural gas in the energy consumption, electricity, and also the share of that. And then, as I said, we have these firm characteristics. And we have this data pre-policy and post-policy. So when we plot our data, what we can see, so here you can see what happened to the oil consumption over time. So 2008, this is where our tax was introduced. And what you see is that already before the tax was introduced, the oil consumption was declining. And the natural gas consumption was increasing, and electricity was also increasing. And then we had in 2010, we triggered the increase in the carbon tax, and also in 2014 again. So this was from 12 to 36 and to 60 then. And so you can already see that there has been some substitution happening before the tax was introduced. But as you can see, those lines really diverge a lot. So there is more happening after the tax was introduced. So what is our empirical strategy? So the main empirical goal is that we are estimating the impact of this time-varying carbon tax on the firm energy consumption and their CO2 emissions. And we have some empirical challenges. So that was the first problem was that we don't have, like in other studies, companies which don't fall under the CO2 tax, because first of all, they all pay the tax, and then some of them can get it back. But there, it's basically, they can self-select. So they can basically decide if they want to have this target agreement or not. So that makes it tricky. So we don't have a control group which doesn't pay the carbon tax. And then disentangling the effect of the carbon tax from other factors. like energy price developments, economic activities, firm size, weather patterns, technological change, policy interventions, sectoral affiliation, and all that is also a challenge. And yeah, so getting this carbon tax effect isolated from all those other factors, this is what we're looking for. So what we do, or what we did, and I'm going to focus on these two, number 1 and number 3, which I have highlighted in red. So the pre-post analysis, here we are looking at time trends and we use firm fixed effects. And so we are looking at the absolute consumption and emission changes in order to find the substitution patterns, and we also differentiate between industry and service sector. And then we also do, what I'm showing to you is we are estimating the tax elasticity of light oil and natural gas consumption, because we would like to disentangle. We want to see if companies react on the tax or if they are reacting more on the overall price, which includes the tax. And then we also did some robustness checks, but I'm not going to go into detail there. So the big questions are, did firms react to the raising carbon tax, and how did they reduce emissions if they reduced any? And so we did this pre-post analysis, and so we are looking at a regression which has the log in energy use or in CO2 emissions. So this is a kind of a dummy where we have yes or no. We have binary indicators for different post-policy periods when the carbon tax was increased, and we control for the size by having the number of employees and the floor size. We also control for weather, economic activity indicators, energy prices, and as I said, we use a firm fixed effect model and have a linear time trend in there as well. So what do we find? So here you can see we have differentiated by the different periods. So the 12 franc period, 2008 to 2009, the 36 from 2010 to 2013, and for 2014 to 2015, when we had a 60 francs per ton of CO2. And as you can see, the consumption of energy decreased only when we are in the area from the very high tax. And what we also see are that the decrease in emissions is even higher, with around 8% reduction in that period where the tax is the highest. Before, we only see like a 3%. And what we see here, we are differentiating between the different fuels. So we see that there is a probability of choosing light oil decreases by 2 percentage points. And the decrease can be explained by a reduction in light oil by 11%. And it's usually substituted then with natural gas in the industry sector. So this shows you the counterfactual development on the left-hand side for energy consumption, on the right-hand side for carbon emissions. And as you can see, so the energy consumption, only when the prices became of the tax became higher, we can see a difference between the counterfactual and the actual energy consumption. But when we look at the carbon emissions, you can see that we see a bigger change, like a bigger difference between the counterfactual and the actual carbon emissions. And when we compare that for an average firm, it was a cumulative reduction over these 6 to 8 years when the carbon tax was introduced of around 25 tons of CO2. So this, the second research question, as I said, I would like to show you or ask the question if there has been a reaction more on the rising carbon levy instead of just of the changes of the fuel prices. As you can see here, so this is the oil price. It was volatile, and so even in areas here where we had only the 12 francs included, we had higher prices compared to the period, like total prices, so the tax plus the fuel price, compared to the period where we had 60 francs per ton of CO2. And so the big question is, are they reacting? So were they reducing emissions even more, although the overall price was lower compared to situations, for example, in the earlier periods where we had very high oil prices. Okay, and so what we did is we separated this effect, and I think, yeah, I'm to be a bit cautious.
Looks like Regina's screen has frozen.
Yeah, it seems we have lost Regina.
Yeah, it had started freezing up. I was almost going to suggest to her to turn off her video just in case the bandwidth was not handling things. So I don't know if our technical person can do anything to help Regina. It'd probably take her too long to log out and log back in.
Yeah, I'll try to check, but yeah, I don't know if I can do much. If it's
I don't know if you
internet
can either.
problem from here.
While we're waiting for Regina to come back, in case she is able to come back, do any members of our audience anticipate having questions for Regina?
With time, but what you can see here is oil or natural gas. So before the price, they usually have a substitution effect, light oil and natural gas. Yes, please.
We lost you a few minutes ago.
Oh, okay.
You were stuck. Do you?
I can still hear you.
Yeah.
Oh, okay.
Regina, maybe you want to turn off your camera for now, just to save bandwidth, just in case it's an unstable connection, just so you can get your presentation finished. Did we? Okay. Have we lost you?
I don't know.
I hear you.
Yeah, I can hear you as well, but I can't see you. So this is a bit weird.
Right.
Okay.
So just continue on. We can hear you.
Okay. So I was just coming to my conclusion, but I don't know what you have heard before. So I was.
You were up to sort of. There was a number 2 in front of. I don't know if it was going to be your findings. I can't quite remember.
Ah, yeah. No, so what we were looking was if the companies were reacting on the tax itself or on the tax. Now something is coming back. Okay. Now I can see you again. Okay. So the question was if they are reacting more on the tax itself than on the tax exclusive net fuel price changes. Because as maybe you have seen that graph where I showed that because the oil prices are very volatile, we had in periods where the tax was very low, we had the tax plus the fuel price was still higher than in periods later on where the tax was very high, but the fuel price was very low. And so we disentangled these effects and we found out that really the firms react more to the tax itself. So because, and there is this, like in other papers, I found the explanation that because they know this tax is going to increase, so it can only stay the same level or it will increase. And the price of oil and gas is very volatile. The companies, when they make an investment decisions, are rather looking at the tax and having in mind that the tax will increase and is already now at 96 francs. They are reacting more to the tax than they are reacting to these net fuel price changes. Oh, now you're gone again.
Huh.
Okay. So we find these two things. So the first thing is that they are reacting to the tax, and it's like an 8% reduction, and that they are usually doing a fuel substitution between oil to natural gas, and that the substitution of light oil with natural gas is mainly happening also in the industry sector, and that they are more reacting on the tax itself. So these are the main findings we can provide from our analysis. Yeah, I'm sorry that you couldn't see it all.
We saw, we just missed a little bit, and you've given it back to us since you've returned. And while you were off screen, I asked the audience if they had any questions, but then you came back, so I'll ask again. Does anybody have any questions for Regina on her presentation? Okay.
Peter,
go ahead.
Thanks. Owen is my name. I'm presenting tomorrow in session 112. But Regina, I saw you cited Anderson there, who has distinguished between price elasticity and carbon tax elasticity. So to my knowledge, he was the first to do this, to separate out the two price, but it looks like you've done the same thing. Is this a new approach from you, or is it well known? I'm just asking the general question.
Yeah, they were doing it, and they were doing it, I think, in the transport sector. So we have used the same approach, but we did it in the industry and service sector. So our tax is a different tax, and yeah, but that's, I think, this paper, and there were other papers. Let me. No, my computer is at the very end. And there were some other papers we have also cited. So if you go on our paper, you can see what is the literature we refer to for this, okay. Differentiating the effect, or disentangling it,
okay, Thanks.
Yeah, no worries.
So we are right at the hour. We can stay on as if people have additional questions. I know Petr did not have a chance to reply to an earlier question and can do so now. If you want to stay on for another 5 or 10 minutes, that's great. If not, I hope you all have enjoyed the session. I think we heard 4 excellent papers, and I hope that the rest of the conference goes well for you. And I hope we meet in person sometime in the future. I do believe I've met at least one person in this session in the past, and I know it's a whole lot better traveling around somewhere like Paris than looking at a Zoom screen, but nevertheless, we're appreciative of being able to do a virtual conference, which we think will be perhaps the last one we'll do for a while. So have a good evening if you're in Europe, or a good day if you're here in the United States. So if anybody wants to unmute them.